Okay, here's the solution to Z5. Z5 gives you a function in table form, but be careful, it's R prime. It's the derivative of some function that's going to be useful. So you read the first paragraph, and there is a whole lot of information there, but perhaps we don't stop and try to absorb all of the information in the first paragraph all at once. So give the first paragraph a quick read. One of the things that might jump out at you is they tell you that the graph of R, now that's R, remember then the table is R prime, but they tell you the graph of R is concave down. It's a curious thing to tell you, so we'll file that away. Also, we don't have to know the volume of a radius or the volume of a sphere given the radius. They give that to us right there. We also get sort of an initial condition here. The radius of the balloon is 30 feet when t equals 5. So that's an r value at a particular time. Remember, this is r prime. Okay, so ready. Part A. Estimate the radius of the balloon when time equals 5.4 using the tangent line approximation at t equal 5. This is very much like question number W6. How do you find the equation of a line? Any line? You need a point and a slope. So we want tangent at t equal 5. So I wish I knew what r was at t equal 5. Oh, look, I do. They gave it to me, 30 feet. Also, I need the slope of r, the function, at time equal 5. That's given by r prime. There it is. So I have a slope of 2 and the point 5 comma 30. So that gives me the equation of the tangent line. They wrote it in kind of a strange form here. But if I plug in then 5.4 in for the time, I will get 30.8 feet. This is a kind of a picture of the situation. There's r, there's the tangent line at 5, and they're asking me to use the tangent line's y value in order to predict, or to estimate, I should say, the function r's y value. So there's a little bit of error, but that's why it's an estimation. Okay. What else did we want to do there? Is the estimate greater than or less than the true value? Well, you can tell by the picture here that the estimate is too big. It's bigger than the function value. But how do I know that r looks like this? Well, it's because they told me that r is concave down. So when I draw a tangent line to a function on an interval where the function is concave down, that tangent line will always ride above the function. Yeah, I think you can see that with a picture. How do we say that, though? How do we give them a reason? Well, you really just have to give a reason. You don't need to justify it. So why is this an overestimate? Because the graph of r is concave down. That's the reason. Okay, so let's go on to part B. Part B is asking to find the rate of change of volume of the balloon with respect to time when t equals 5 and indicate units of measure. The rate of change of volume of the balloon with respect to time. So I need to think about volume. Here is a volume formula, but it's not rate of change of volume with respect to time, it's just volume. How do I find the volume, or how do I find, I should say, the rate of change of volume with respect to time? Well, if I can manage to find the derivative of that with respect to time, that would be dv dt, that would be the rate of change of volume with respect to time. How in the world am I going to be able to find dv dt? Well, what if I take the derivative of both sides of this equation with respect to t, with respect to time? This will be dv dt, and this is the sticky side. Remember, r is a function of time. R is a function of time. As time goes on, boy, that was a terrible arrow. As time goes, that's an arrow the wrong way. As time goes on, there we go. R doesn't really help. Changes. So I need to take the derivative of that with respect to time. Just think, r is a function of time. I need the chain rule. It's really implicit differentiation. So I can talk about it all day long, but that's what you need to write. This is both sides of that equation with the derivative taken with respect to time. Notice the chain rule. Derivative of the outside, derivative of something cubed is 3 something squared, and the derivative of the inside, well, is dr dt. What are they asking me for? They're asking me for dv dt. If I knew what r and dr dt was at time equal 5, I'd be all set. And guess what? I do again. R is 30 feet, that goes in for R, and dr dt at time equal 5 is 2 again. I get that off the table. So a little bit of arithmetic later, and you get that problem. Okay, C, use a right Riemann sum. We don't use that language a whole lot. We didn't in class. We should probably. That's a right rectangular sum. Okay, so we want to use rectangles. A right rectangular sum with 5 intervals indicated by the data to approximate the area, or to approximate the definite integral from 0 to 12 of r prime. So I need to find the integral of this function right here, r prime, on this interval, the integral from 0 to 12. So I'm going to make rectangles. And what kind? Right ones. So this is a rectangle right there. Those are the 2 endpoints. I'm going to use that, the right one, for the endpoint of the first rectangle. The second rectangle goes from 2 to 5. That's what delta x is for the second rectangle. And I will use 5 for that endpoint. Of course, what do I mean by using 2 for an endpoint of the first rectangle? That means I use 2 to find the height of the first rectangle, which is r prime. So there's the height, whoops, terrible arrows. There's the height of the first rectangle. There's the height of the second, the height of the third, the height of the fourth, and the height of the fifth. So we do get 5 subintervals. Good. Take all of those heights, I have to multiply each one of those heights by delta t. So 2 minus 0, 5 minus 2, 7 minus 5, respectively. So all of that, gather all of that, make sure you write that down. This needs to be written. Okay, they need to see all of those plus signs, all of those products, and we want to know, now this is really fancy, that it's approximately equal to the integral that we are after, the integral of the function r prime. So you don't necessarily have to write this part, but they do have to see your work. Okay, so that's the value, 19.3. How do we get feet out of this? What are the units here? Well, what are the units? This is basically unit multiplication right here. The units on r prime are in feet per minute, but don't forget, dt also has units. That's a little change in time, so that's measured in minutes. So feet per minute times minutes, that is in feet. So they're trying to give you a clue here as to what this means. What is this? Well, what do you get when you integrate a rate? You get the change. This is the change in r, this integral. That's what that means. I'll say it again. When you integrate a rate, you get the change in the original quantity. This is the rate of r. Sorry, just r prime. That thing right there is the rate of change of r. So if I integrate that, I get change in r. And between those two times, time equals 0 and time equals 12 minutes. So each one of those things, the answer and the explanation were each worth the same amount, each worth a point. All right, last part, D, is your approximation in part C greater than or less than the actual area under the curve, the actual definite integral? So I said area under the curve. That's probably the best way to interpret that one for this part, that definite integral. That definite integral is the area under the curve of r prime. And what do we know about r prime? We know r prime is decreasing. It's getting smaller. Is that right? And do they actually say it in here? Okay, so I'm not finding where they say that r prime is... Oh, r prime has to be decreasing. There it is, because r is concave down. That means r double prime is negative, so r prime is decreasing. I'll say that again. That's a little complicated. Since r is concave down, r double prime is negative. That's what concave down, and that's the connection between a function's concavity and the second derivative. So because r is concave down, r double prime is negative. Now r double prime is the derivative of r prime. If r double prime is negative, that means r prime is decreasing. So I don't know necessarily that r prime is concave down, but I do know that r prime is decreasing. And it doesn't take too many rectangles to see that if I use the right boundary for each subinterval to determine the height of the rectangle, those rectangles will always be below the curve. So this is an underestimate. The Riemann sum, the right rectangular sum, is an underestimate of the actual area under the curve because I'm missing these little bits of area in here. Okay? So, what else do we need? Give a reason for your answer because r is decreasing. You'd have to justify, since r is concave down, r prime is decreasing. All right. And did they talk about units? Units. Oh, okay. So this isn't really math here. This is scoring. You get 1 point for using correct units in both parts B and C. So in parts B and C, you'll notice they say indicate units of measure using correct units. You had to get them both right to get that last point. Okay, so that's all for Z5. Thanks.